Oh, what's good? What's good? Let me just make sure everything is working. Um, okay, yeah, good. All right. Also live on YouTube. Infinity. Look, this problem. Cocoa eating bananas. You are given an integer array. Piles. What piles is the number of bananas in the ith pile? Okay, so that means there's one banana in the 0th pile. There's 4 bananas in the first pile. Okay. We are given an integer h, which represents the number of hours. You have to eat all the bananas, okay? You may decide your banana per hour eating rates ratio is k. So each hour you may choose a pile of bananas and eat k bananas from that pile. If the pile has less than k bananas, you may finish eating the pile, but you cannot eat from another pile in the same hour. So return the minimum k that you can eat of bananas within h hours. Okay, so without even looking at the explanation, I'm gonna say, okay, so you have 9 hours to eat how many bananas? So 5 plus 3, 8 plus 3, sorry, 8 plus 2, 10. 10, yeah, so you have 9 hours to eat 10 bananas. So that means you can do 9 over 10. Okay. We're saying we're eating with an eating rate of 2, so 2 hours. You can eat the bananas in 6 hours, okay? Yeah. With an eating rate of 1, you need 10 hours to eat all bananas here, which exceeds 1, right? Exactly. Thus, the minimum eating rate is 2. Okay, yeah, that does make sense, right? So, for example, if we were to eat 1 banana per hour, right, that would be 10 hours. But 10 hours already exceeds the 9-hour thing, right? So, what we could do is, I think simple math, like 10x equals to 9. And what do you say? Is it 10y equals to 90? Then we want to find is realistically there's simple math in this to understand what's going on first. Hi Fame, how you doing? Uh, okay, let me try to look through this. So then I'm gonna try to so let's build another the minimum eating ratio. So for instance, we have so 1, 4, 3, 3. Also, I focus on where. Oh, hi, Fiat. Is that how you say Fiat or Fate? My bad if I'm pronouncing it wrong. Where? Each pile. And what was it again? Which set even is it about? It's okay. Would you mind like typing it out like how you pronounce it? Because like I have also a unique name and I don't like it when people mix it up. So I would appreciate that. But if you don't want to, it's fine. Each. Okay, great. So for example, what is equals to, so that means the sum of piles here. Sum. I'm solving this question on LeetCode. It's called Cocoa Eating Bananas. Do you know what LeetCode is or LeetCode? So far is what 10. So far is equals to 10. What was it again? So with the leader of the one, we would need 10 hours to eat a banana of the other which exceeds this. So yeah, so then and if we decide to eat. Okay, so LeetCode is essentially like um is a set of questions that prepares you for software engineering interviews, but the technical aspects. So, like for example, if you're going for like a software engineering interview or like a job, and they ask you to like they expect you to code, this is like the best way to prep for it because it teaches you about the concept of data structures and algorithms. So, a data structure is essentially a way of managing, processing, and identifying data collectively. So for example, if you want a sequence of numbers stored in some form of data, you put it in a list. If you want to have one thing meaning another thing, you put it in a dictionary. So that's like key pair values. If you want if you want um determinants of how to search something, you could put it in like a tree, like a data structure called a dynamic, it's like a binary search tree, things like that. It's dependent on how you represent data. Like for example, the logic behind like maps, like the Google Maps and everything, is through graphs. So a graph is like a connected list of nodes in different formats that's most likely going to be undirected. So if you want to go from, let's say, New Jersey to New York, you would have to use kind of like a graph. The underlying data structure is a graph for that. Now you're good. What's like your domain? Like, what do you do? Like, are you still in school? Are you still? What's up? Okay, that's all good. Um, okay, check it. Okay, so let me get back to this question. Sunflowers because when we decide to eat. So that's a no-go. So that means we need to, and is, are we supposed to only return? Oh, it's an integer. Okay. So we can't return a decimal. So for example, that's so for example, that's 10 divided by 10. So, yeah. So, for the hour. The iterative tree and then is how though? Is it going to be 5? Because well, I mean, doesn't technically because you're doing yeah. So if I do 2, so then I can this and then this and then that. Well, let me see. Let me see the same logic for this. So for example, we have 25, 10, 23, 4. So 25 plus that's 35. 35 plus 23. That's what's 35 plus 23. 35 plus 58. 58 plus 4, that's 62. So obviously we can't do 1 per hour because that'll be way ahead. So we need 4. We need at least that, right? So if I do 62 divided by 4, what would that give me? Do I have to download the calculator app? Or that'll give me 15.5. Okay. So that means if we did 16 per hour then. So why is it 25? I'm so lost. I'm kind of confused on why. Oh, what's your major? I'm kind of confused. I don't think we decide okay. Oh, okay. Kind of. I think I get what's going on here. So I did 25 per hour. The 64, right? Or 62. So if I didn't do 62 divided by 25, that's 2.48. All right. Okay. So technically, isn't it low-key just like the technically isn't it just the minimum value in the piles because or well not the minimum because we couldn't do oh okay so what we could do is because okay it's either going to be the minimum value in the list or So we did. I think we checked first with the minimum value. So we can do. Man said just put banana. That's crazy. So we can do so. I think if we do something like after doing that, if and we use that as the rate first. So for example, minimum value equals here to 1. And if we do that as the rate with each one pair, so then we would do like, okay, so so that would be something like, so for example, let's say, so for example, 1, but then 1, that would be 1, right? But then 10 divided by 1, so it would be, um, uh, piles over in, and then if that is greater than, that is greater than h of x, that's nice. So we just, yeah, I think I think that would be the logic. No, but then, so for example, if we did, then that wouldn't make sense because if you think about it here, then we'll start from 4. But then 4 divided by 62, that's obviously way more. Then we'll go, okay, 23 and 10, then 10 divided by 62, that's more, okay. Then we go to 23, 23 divided by 62, it's 2.69, okay, that's the minimum so far, which kind of does make sense. Oh, kind of does make sense. And then 6 divided by, well, 25. That's 2.5. Yeah, right, 2.5 is smaller than, yeah, exactly. Okay. Yeah, okay, so logically, we could just have like an array. Logically, we could just have an array of um every single number in the pile divided by the total number of the pile, and then just find the minimum value of that. Okay, yeah, that does kind of make sense. Okay, wait, chill. What the heck? So we could actually just what we could do is we could need a ratio, and it doesn't say we have to use. It doesn't give us a specific time complexity. Okay, so we could use a ratio list, and then that calculates the total divided by file I, and then return the min, or yeah, or grab the min and then find the closest to it. So for example, or find the index. Okay, so return the, but yeah, find the index of smallest ratio, return file corresponding. So what I mean by that is, for example, we have, so for example, we have 1, 4, 3, 2, right? So in our return list, so it's going to be 10 divided by 1, 10 divided by 4, and 10 divided by 3, and 10 divided by 2, right? And then this is going to give us, it's going to give us 10. It's going to give us what's like 2, like what, 2 point something, like 2 point something. 2.5, yeah. 5, and then 10 divided by 3, that should be what's 0.33, or 3.33, yeah. 3. And with this, it's 5, right? Oh, okay, so by this logic, that doesn't even make sense then. Because it wouldn't work. Because then this will be turned to this, but then 4 is not the answer. Because it's 2 that's the answer. Because if we did, says you're also given 100% of the you decide when to okay. Wait till I get to the call. How many minutes have I spent on this? 20 something minutes so far. Boring. Well, I know. How many minutes do I on this? I don't know why I'm struggling to understand this. It's not supposed to be hard. Yes, let's see. That's something here, but I'm not sure if take out. Okay. That's why I don't get it here. Like, for example, I think I get it here because, okay, 25, if you eat 25 every single time, obviously, at least that's the maximum, right? So it's not like you're not finishing a pile every single time. I get that one here. But with this one, it's like you could use 4, you know, and then you could use 4 here again. You could use 4 here again. You could also use 4 here again. But you decide to use 2. Oh, but it's the minimum out of all of those ones, right? Okay, so that kind of does make sense. Okay, so okay, so what we could do is okay, but then H here is 9. So realistically, so then we could just then filter it to. Okay, I think I get the method now. We could also just then filter it to the maximum out of this one. But let me try that for this. So for example, 25, 5, 10, 23, 4, right? So that means that would be, this is 62, right? So 62 divided by 25, 10 divided by 25. 23 divided by 25, 4 divided by 25. Right? So this would be 60 divided by 25 is 2.48. Then 10 divided by that's gotta be like 2.5, right? Or 0.25. I'm sorry. Oh, it was just so sorry, 0.4. My bad. 0.4 divided by 25. That's gonna be like at least 0.92. 4 divided by 25. 0.16. Okay. So, what's the hour again? The hour is 4, right? Okay, so yeah, my logic works. So it's technically the highest. So it's technically the highest. The index of the highest divisible this is crazy, but the index of the highest divisible that is lower than h. It's quite weird, but so it's technically index of the highest divisible. So would so what we do here is okay, we could init the ratio list that calculates that over that, and then loop. So have we can do this more efficiently, but I just wanted to go brute force first. Have a or technically max in this scenario, max val. I know it doesn't mean, but technically max val. Um, and then we'll say we can then say find the index of the biggest ratio, biggest ratio that is smaller and return the index of the number in which that index maps to height. It's probably not how I'm pretty sure he did it, but this is kind of how my brain is working. So what that would look like is this. It took how many minutes for me to figure that out? 29 minutes or 25. Crazy. But okay, so we have our result for the ratio. We'll call this. Um and we could also do what we could do sum or list. I could actually use higher function. I could practice in my head function stuff in here. List sum will be still work on sum of items. And then ratio will technically be list map. Right? Yeah, map. How does map work again? It's the thing, then the function, then the iterable, right? How does map work again? Function and iterable, yeah, that's correct. Yes, it's function. So it'll be the x, and then x would be Technically, some the list sum. Right. This means that I just put everything in there, right? List sum divided by x, right? Let me see how to use it again. Let me just make sure. Yeah, x times x times 2, right? Yeah, x is equals to x times 2. So that means, yeah, this times this times that. Yeah, exactly. So x is everything in the list. Yeah, okay. Yeah. So, yeah, we can leave it in the decimal. I don't mind. Where it is, then we'll keep this here, and then we'll do the name of the function, which is going to be, well, piles, right? Yeah, piles. So this will give us the ratio. So reduce it. Oh, UK uses ratio. Okay, and after that, so we have that ratio now. Then technically we just need to loop through, um, technically we need to just loop through that list. We need to loop through ratio and find the smallest, the biggest one that is not biggest one that is smaller than h. So I'll do this manually. For x in max is equals to minus 1. Let's put that there. For max. Wow. So it'll be then for, um, we'll do I comma val and enumerate, what was it again? Piles. Okay. I comma val and enumerate. We could then do, if val plus h greater than max val, max val. Realistically, we could just do this. If max elimination, we could do max val is equals to the max. So, because that's a condition, we do that there. And then, yeah, and then we should just return. No. So we got the max val. Then we need the index of that. So, and then we do max val index. Index, which is going to be, let's go minus 1 here. The max val index is going to be, it's going to be equals to I. So now that we have that, then we now just need the index. So it's going to now just be returned on files max. Wow. Yeah. It's very confusing, but let's see if this works. Map must have at least 2 arguments. It doesn't have that. Oh, my bad. Let's see. Okay, so it worked for one. It worked with this. Yeah, cool. For this one, it didn't work. My output was 4. Oh, sorry. This one it was 25. Let's see why it didn't work for this one. Let me move to it. Let's see. So we have. Oh, yeah, plus I'm supposed to even change this from EA Sports FC to this. Forgot. Let me check. Alright, that's cool. Okay, so why didn't this work? This didn't work because it didn't work because okay, basically it's the other way. So if macros. Oh, it's in power. No, no, yeah, power is also H. Oh, I see. No, it doesn't necessarily have to be. It's sorry, it's it's the ratio, not the vowel. Yeah, so if it's if piles on about ratio I right, yeah. Yeah, it's this as yeah, not that. So let's run it back one more time. Okay, we got 23. That's close. That's closer to the answer. Um that's 092. Oh, sorry, what the heck? Yeah, 25. So this would be one. Bro, what am I doing? Bro, so this 162 minus. Wait, how did I do it again? Yeah, yeah, I think. Bro, 10 divided by 10 and 62 divided by 43 and then 62 divided by so we could do it right around 10. Bro, what is wrong with me? I have 6.2 obviously. 6.2. 2, yeah, 6 divided by 23. That's 2.69. 6 divided by 4. 3.5. So yeah, if that ratio is less than H, yeah, and yeah, there we go. Yeah, so if that ratio is less than H and that ratio is less than H. Oh, then we're supposed to get the minimum of it, right? Oh, so in this case, it's getting the minimum. Oh, yeah, okay, in this case, yeah, because this and then this. So in this case, this was getting the maximum. Uh, like in this case, it's getting the minimum, in this case, it's getting the maximum. This is not helpful. Because I think we're so close, but we're missing something. I get what's going on here, man. That's what I don't get is like when they say with an eating rate of 2, you can eat 6 banana. You can eat the bananas in 6 hours. How? Like, so for example, what the only thing that has to do with 2 and like 6 is not 12. But this is, yeah, so like how are they even getting? Are they doing like okay per hour is what 60? Like I don't get what's going on. 'Cause I don't want to just give up easily. How many minutes have I spent on this? I spent okay 45 minutes. If I don't get it in 5 minutes, then I'll have to. Oh no, man. This is the part that's confusing me because how did I get here? So anything in a one, you need 10 hours. Yeah, but with an eating rate of 2, so if you eat 2 per hour, right? So that means okay, you're eating 2 per hour. That's what. So that's okay. Gone. Okay, 2 again. That's gone. Then you need another 2 again here to go. Then 2 again. That's gone. Then you need another 2 again for the remaining one. Then 2 again here again. So it will be okay. Let's break it down. So it will be in the one, it'll take 2. That's fine. It's gone already. And the 4 one, it'll take 2, but it's 2 remaining. So it's take another 2. Then 3, it's take 2. Then you also take another 2. Then this 2 will only take 2. So that's 1, 2, 3, 4, 5, 6. Oh, okay, I get it. Oh, okay. We actually sit down and yeah, okay. I kind of get it now. I kind of get it now. Okay. So 25. They go 1, 2, 3, yeah, 4, yeah. And if you get it right on time, if you get it like exactly on, yeah. Um, okay. So if you then, yeah, I think my first approach was even more correct. Where like, okay, you first do if the whole thing, then you try one, then you try two, or you could get multiples. I guess you could do multiples of. I think that might be it. Just do multiples or factors of that number. So for example, you could do um. So for example here, right? So it's 10, technically 10, right? Okay. What are the multiples or things that 10 can divide itself with? So obviously 1, but 1 is not going to cut it. 2, that's fine. 3, but if you use 3, right? For example, if you use 3, that'll be easier, right? Because, okay, 3 here, okay, 3 here, and another 3. Wait, think about it. 3 here, then another 3, and 1 3, and then 1 3 here. So that's 1, 2, 3, 4, 5. 4 times, so 3 times 5, that's 15. Or actually, what do I mean? Sorry, not 15. Sorry, we're not counting it down. It's 1, 2, 3, 4, 5. So that's 5. So you could actually do it in, you know what I mean? 5. Then that one was 6. I think there's I'm getting closer, but there's a fine line between, oh, I don't know one. So for example, yeah, with a rate of like 25, I get it right. So 1, 2, 3, 4. Alright, so you will just need 125 here, 125 here, 125 here, 125 here. Right? So that's 4. And it's within that. Cool. But if it's 2, so if I did 23, right? If I did, okay, 123, so I'll need two 23s here, 123 here, 123 here, 123 here, right? So I'll need, yeah, exactly, right? So two 23s here, 123 here, 123 here, 123 here. So it's 1, 2, 3, 4, 5. That's 1, 2, 3, 4, 5, right? So that took me 5 times, but this one took me 4 times. So 4 is, yeah, I guess 4 is obviously, better, right? But in this scenario, right, if you're using 3, they're able to use less threes, but two is like there's always a contradicting. I don't know. There's always a contradicting factor with whatever implementation I go with. But I do get the whole 6 hour thing though. It's like okay, so two, two again, two again, two, and I get 25 years. Yeah, but like finding the minimum of that is what is the problem because okay, if it's the minimum, then minimum in what aspect? Minimum integer k. The minimum in Yeah, so exactly. So the minimum interact key for this is actually 23, not that because you could do this. Oh no, you can't, right? Because yeah. Oh no, okay, so it does make sense. My bad, my bad. I think I get it now. Because okay, if I use 23 here, then it to be fives. Well, 5 is greater than this, right? Okay. Okay, so I think I can figure it out now. So for example, we're doing two. So we're using. I think we use factors, right? Okay, so let me scrap this. Let me take this out first. We're gonna use factors. Right. So for example, it's 10. So factors of 10 is what? Um, 1, 2, 5, and 10. Right. So we get the factors. And then we try each of these factors and see how many times it works. So for example, we'll do 1, but then 1, 2, 3, 4, 5, and 1, 2, 3, you know. So want to go here ones, but want to go here 1, 2, 3, 4. Want to go here 1, 2, 3, 4. Want to go here 1, 2, 3. Want to go here 1, 2. So that's obviously not efficient. So I think we should just even be skipping 1 step. Then if we do 2, 2 go here, correct, yeah. 2 go here once, twice. So what we're kind of doing is like we're kind of like dividing. So for example, we're finding the margin. No, we're dividing, and if it's like 1 divided by 2. So if 1 divided by 2, if the division of that is less than, you know, is less than 1, then we just put it as 1. Yeah. So for example, this is 1, 4, 3. See, right? So we're using 2 as like k, right? So that means 2 have to go here. 2, let's go here 1, there 1. Then 2 have to also go here 1, then 1 again, and then 2 just have to go here 1. But what I mean by 1 is like it strikes out. Like, yeah. So if you count all of this together, 1, 2, 3, 4, 5, 6, that gives you 6. So that means 2, and is 6 less than, yeah, so you can do that. So how we're gonna like write this in code now, because I'm even trying to like understand it is weird. So it's gonna be something like, um, so okay, I'm trying to visualize what am I actually doing. What I'm doing is I'm using a factor, so I'm going factor by factor, a factor of the length of the whole list, right? To see how many times it could divide that number in the pile, right? And so for example, 2 will go here, let's just say 1, right? Okay, fine. It goes there. 2 will go here 2 times. 2 will go here 1 plus something. So that's already automatically 2 times. And 2 will go here 1. So what we're technically doing is we're dividing it by that, and if it's greater than, so we'll first check, okay, if it's less than the number, we just put it as 1, right? And if it's greater than the number, then we check, or no, it's not even about greater. If it's greater than the number, then we check, okay, how many times can it go into it? There's more than 1. So for example, it's so it'll be 2 here, so to go here. So it's because you need 2 to take out the 2, and 2 to take out that one again, which is fine. So then to go here again, you need to take out the first 2, and you also need that 2, and then you just need 1. Uh, so how we're gonna do this is a problem. So this is gonna be okay. So or, if Fill it. Post. Let's say put P or put it F. So if F, so if P divided by F is, so first if P is less than F, then we'll just put it as like, just like return one, essentially. But then if P is less than or equal to that, if P is greater than F, right, then we're gonna return 1 plus, we'll return the mod, whatever, so we'll do P divided by F plus, um, 1, technically, yeah, because, P, basically that's, yeah, and then it would just sum that list. And if the sum of that list, and so if the sum of the list is less than H, then we update the update. Okay, so for example, this is 62. 25 is not a factor of 62. So that logic will never fucking work. So 25, right? Yeah, 25 is not a factor of 62 because it doesn't even work. But what is a factor of 62? Let's see, factors of 62. It's 1, 2, and 31. And 31 is not in that list. Bro, my head is gone, bro. The hints, bro. Given H is yeah, bro, my head is already gone. So I'll just look at the solution, bro.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve Coco eating bananas. But before we do, I just want to say that if you do have any requested problems, you can feel free to leave those in the comments. I do have a large backlog of requested problems that I'm working through, so it may take some time for me to get there, but you can feel free to request at any time. And if you find this video helpful, don't forget to leave a like and subscribe for more videos. So this is a pretty interesting problem because there is a brute force solution that we can arrive at, and that brute force solution can easily be transitioned into a binary search solution, which is the optimal solution for this problem. So we're going to be working our way from the brute force to that binary search solution. So Coco loves eating bananas, and we have n piles of bananas given to us in a piles input array. We're also given a second parameter, h, which is the number of hours that we have in order to eat all of the bananas. So we have to eat them within h hours. And so Coco has a certain eating speed where she can eat a certain number of bananas per hour, and that variable happens to be k, and k is not an input variable. That's what we're trying to determine as the solution for this problem. Each hour, she can only choose one pile of bananas and eat k bananas from that pile. So that's what we're trying to determine, that k value. If the pile has less than k bananas, she'll eat all of the bananas, but she's not going to eat any extra bananas from a different pile. So what we're saying here is Coco can only eat at most one entire pile of bananas in a given hour. So what does that tell us? Already we're given some key information. Let's say we're given a certain number of piles, right? So basically the length of p, h must be greater than or equal to the length of p. Why is that? Because let's say we have 5 piles, right? So let's say we had 5 piles, and let's say this is what the piles look like. The values aren't too important, right? 1, 1, 2, 2, 3. And let's say we had h equals 4 hours. Well, let's say k equals some really big number, like 3, right? Basically the max of this input array. Okay, Coco ate this entire pile, Coco ate this entire pile, this entire pile, and this entire pile, because she could only eat 4 piles because we only have 4 hours, right? Coco can only eat 1 pile per hour. So if she ate all 4 piles over here, we'd still have 1 left over. That's why they guarantee us that h is always going to be greater than or equal to the number of piles. So the minimum in this problem, given this input array, h, the minimum it could possibly be is going to be 5. And I sort of wrote over it, but the last important thing that they tell us in the problem is we want to determine that eating speed k that Coco is going to eat at, but we want to know the minimum integer k, the minimum eating speed of Coco, that she could eat all of the piles in exactly 5 hours, or exactly whatever that time interval, that number of hours happens to be. So let's take a look at this example. They give us an input array of 4 piles, and they give us 8 hours to eat all 4 of those piles. What's the minimum k, the minimum eating speed that Coco could use to eat all of these piles in at most 8 hours? So we have to eat all the piles in 8 hours or less. Well, the brute force would be to start at 1, right? Because Coco could try k equals 1, right? Can we eat all piles in 8 hours then? Well, it will take us 3 hours to eat the first pile, right? 3 divided by 1, which is our k, right? 3 divided by 1 is going to be 3 hours to eat this first pile. And to eat the second pile is going to be even more. That's going to be 6 hours, right? 6 divided by 1, 6 hours. So far we already have 9 hours, and we haven't even eaten the entire number of piles. So therefore, k equals 1 is not going to work. And we could just continue this brute force approach, right? Now try k equals 2, right? And then do the exact same computation with k equals 2. Now, my question to you is, we know that the minimum possible solution would be k equals 1, right? K can't be 0 because that would mean we're not eating any piles. So the minimum is 1. What's the maximum that k could possibly be given this input array and given this number of hours? Well, remember, the number of hours is always going to be greater than or equal to the number of piles. So in the worst case, k would basically be the max number that happens to be in our piles. For example, if k equals 11, right, that means we're able to eat the max pile in exactly 1 hour, right? And if we can eat the max pile in 1 hour,
So
that
we can
means
eat
every
everything.
other pile is also going to take us only 1 hour. So therefore, we're going to eat every single pile in 4 hours. And we know for sure that this is going to be less than whatever is given to us as h, right? We guaranteed that at the beginning. So really what we're doing here is we're going to try every single value from 1 all the way up to 11, which happens to be the max value of our piles. And the first value that we get that allows us to eat every single pile in less than or equal to 8 hours is going to be our output. So we're going to end up trying 1, we're going to end up trying 2, we're going to end up trying 3, and we're going to find that 4 allows us to eat all the piles in less than or equal to 8 hours. So this is not a terrible solution, right? Even though we're brute forcing the entire solution set, 1 through the max of piles, it's not going to be terrible. What's going to be the complexity of that? Well, we're potentially going to have to iterate through every value in this potential solution set. What's that going to be? Well, 1 through the max value of our piles, right? So it's going to be, let's say, big O of the max value of piles, so max of P multiplied by the length of P, because for every K value, we're potentially going to have to try, okay, if I eat all these, how many hours is that going to take me, right? So we're going to have to iterate through this entire array for every K value that we try. So we're going to get a time complexity of max of P multiplied by P. Right, but that's only, we're getting this max P from the fact that we're having to iterate through every single value in this K range. But why should we iterate from 1 to the end of that K range? Why, in which case, in the worst case, we'll have to go through every single value. Why don't we instead apply binary search on this K range? What's that going to give us? Well, we can reduce max of P to the log of max P. So if we can improve this, this is what our time complexity is going to be. Okay, so I ran out of room, but this is the improved time complexity. Basically, we're taking this variable and applying a log to it, which is going to reduce it a little bit. So let me show you quickly how that binary solution is going to work. It's pretty straightforward, and then we're going to jump into the code. So we're going to be using binary search. We're given this input array, and we want to eat every single pile in less than or equal to 8 hours. So we know that the potential rate that we're eating bananas at, K, is going to be between 1, that's the minimum it could possibly be. The max it could possibly be is going to be whatever the max in our input array is. We know the max value is 11. We can find that in linear time. So then we're going to initialize a range like this, right? This entire range that we have going all the way from 1 to that max value 11. So in other words, we're going to have a left pointer at the minimum and a right pointer at the maximum. Then we're going to compute the middle by taking the average of left and right. 1 plus 11 divided by 2 is going to be 6. So our middle is going to be here. In other words, our K that we're trying is going to be here. This is the rate that we're going to eat bananas at. So we're trying the rate of 6. Does this work? Can we eat all these bananas with a rate of 6 bananas per hour in less than or equal to 8 hours? Can we do that? Well, how many hours does the first pile take? Well, 3 bananas, right, divided by the rate, which is 6, is going to round up to 1. That means it took us 1 hour to eat the first pile. The second pile, 6 divided by 6, is also going to take 1 hour. So let's just count the number of hours. So the second, or rather the third pile, 7 divided by 6, is going to round up to 2. So that's going to take 2 hours. The third pile, 11 divided by 6, is going to also round up to 2. That means 2 hours. So we just did this in 6 hours, right? Is that good? Does that mean we found our solution? Well, 6 is less than or equal to 8. That means we were able to eat this entire thing in the time threshold with a rate of 6 bananas per hour. Is this our solution? Well, remember, we were looking for the minimum K value that allowed us to do this. So this might be the solution, but let's try all the smaller values, or let's start our binary search in this direction to see, is there a smaller value than 6 that we can use for our K value? So basically what I'm doing here is, if we're able to eat the entire pile in the threshold, what I'm going to do is then start searching in the left direction. So what I'm going to do is take my right pointer and shift it to K minus 1, because now we're searching this entire range. What if the opposite was true? What if I tried this K value, but I was only able to eat...
I think I get it now. So, correct approach. You want to since the values in the pile are bounded by the values, and we are sure that you can eat all of them. That's piles, then what was it again? Perform binary search on that. Perform binary. Wait. Hi, Brian. How you doing? Okay, so yeah, so we can find the maximum number in the list, which is going to be we need to essentially generate a list. So we'll call this acceptable numbers. So what can I call this? Let's call it possible case. Possible case. That should for this one. Yeah, that's so. After doing this, we need to then use all of this or perform binary search. So with so what that means is so maybe this is possible. Yeah. So it's hard to do. Just double divide them. Yeah, because you need a index again. No, so let's say okay. And for all of this, then we can now say um or is it or B and B files. Let's put banana in files. To check. Oh yeah, then I'll need my own, how do you call it? It's page. Right? Yeah, I should put that outside. That's gonna be um well, okay, what you got? Right. So if yeah, so piles and I said piles or pile? Piles, piles it's more than no, another possible case smaller than and this is the term smaller than else we want to do divided by what did I write? I need some Also, yeah, so B divided by that, sorry for that. One. And at the end of this, I need to check. So, no, whatever I need to do is some of that. I already did the sum there. Yeah. So I also did a mean. So onion. So the rents. Yeah. Right. What's it again? And, no, yeah, weird. It's smaller than what it going. Is this then is no, sorry, I think it's still then H actually right here. And which is one yeah, and then I just right, yeah. Okay, let's say close to so on. Anything else. What is a position where to be close to? In a situation where to be close to. Thank you. Yeah. That's one. Yeah. So after doing this, sharpen when it's found, you know. No, we need to also update our update. Oh, and possible occasions and at the end of this one, Running search, so we get in the middle, yeah, which is gonna be 6. And then 0, so for we in piles, this here, if possible, and which is this, is less than or equals to B, is plus 1. But if it's greater than B, then we're just gonna do, so for example, right here, it's gonna give you 1, then plus 1, yeah. But if it's like, 3 and 3, let's see, whatever. You know, and then it will do that for every single one in the piles here, and then into, at least by the time to give you, the temporary H. So for example, to go here, is 1, right? Yeah, so we're chilling. It's 6, right? Yeah. So whichever one is, we'll do 1. Here is the exact same thing. So plus 1. Here it's 1 plus, it's gonna be 2. There's gonna be here. That's gonna be 2 again. So 1. So 1, 2, 2. That's 4. And that's 6. Okay. Yeah. Better than 6 hours. And 6 is lesser than 8. Right? Yes, that's gonna be this. So to move this temperature, so that yes. So we're gonna move here right to here. Yeah. And then, yeah, I got it. So let's do this one. Draw 1, this one is 2, 1. I'm just only again 1 instead of 1. So 0 to 21. Hmm. Um, Oh, yeah, what the heck? It's the other way around. Oh, three. Oh my God. Got it. So let me try another thing. What's the second? 1.32. Probably the one on mine. Yeah, okay, wait. Oh my, okay. Great job. So, modifications we have to do here is it was the other way around here. This, this, and then scrap this. Alright, so this is plus. Good error. Line 11. Good. Runtime error. What the heck? UI will make it. Gotta go like 30 and like 4 minutes because I have to each sequence class. Yeah, it's gonna take a while for this one. Though. I thought it was gonna break my computer. Damn. Yikes. Okay. Thank you for counseling. Okay. And we can just have an edge case here saying send me so let's not. Man, I don't know. I don't know. I don't know. We'll come back to this question later. I have to go eat. Probably answer's probably there, but I just don't want to look at the answer because I'm not learning like that. My can close though.